Hello everybody. In this video we are going to derive the expectation and the variance of log normal distribution. Let y be a random variable that is equal to e to the x, where x is normally distributed with the parameters mu, sigma squared. Here we are going to use the fact that a random variable is said to be log normal if log of it is normal random variable. So if we take ln on both sides, ln of y will be equal to ln of e to the x, and ln of e to the x using the logarithmic rules equal to x, and our x is normally distributed. So expectation of y will be equal to expectation of e to the x, and expectation of a function by definition is equal to the function times the PDF integrated over the domain. Here our function g of x is e to the x, and our PDF f of x is the normal distribution PDF because our x is normally distributed. So we can set our integral from negative infinity to positive infinity because that's our domain, e to the x, which is our g of x, times f of x, which is our PDF, sigma times square root of 2 pi e to the negative x minus mu, the quantity squared, over 2 sigma squared dx. First of all, for simplicity, let's take mu as 0 because mu is just a number and we can pick up any value we want. In this case, we are finding the expectation of y, that is log normal with the parameters 0, sigma squared. And we can use this fact for the general. Let's find the expectation of y with the mu 0. If mu is 0, our f of x will be negative x squared because this is 0. So let's rewrite. Now we have this integral to compute. Using the exponential rules, we can merge e to the x times e to the negative x squared over 2 sigma squared. Let's do a side work here. E to the a times e to the b is equal to e to the a plus b. So we need to add the exponents. So our exponent here x plus negative x squared over 2 sigma squared. Now we can merge this fraction using the fact that a minus b over c kind of term is equal to a times c minus b over c. In our case, this is a, this is b, and this is c. So our exponent will be 2x sigma squared minus x squared over 2 sigma squared. And we can factor negative sign on the numerator, so we obtain positive x squared minus 2x sigma squared on the numerator, and our denominator is 2 sigma squared. Now we can rewrite everything. So expectation of y turns into integral from negative infinity to positive infinity, 1 over sigma times 2 pi e to the negative x squared minus 2x sigma squared over 2 sigma squared. This term on the numerator here is almost look like a minus b, the quantity squared, which is a squared minus 2 times ab plus b squared, with one small difference. We don't have b squared term here. So we can add b squared term here and subtract b squared term here, that we don't change anything, but we can rearrange it by compacting a minus b, the quantity squared. So let's rewrite everything. So in this case, our A term is x and our B term is sigma squared. So sigma squared will be sigma to the fourth power. And we need to subtract sigma to the fourth from the group. I use positive sign here because the first sigma is negative when we distribute. And our denominator is same, 2 sigma squared, and we have the x here. This is our side work here. Now we can compact this in the parentheses using a minus b squared. So expectation of y will turn into negative infinity to positive infinity, 1 over sigma times 2 pi. E to the negative a term is x, b term is sigma squared, and squared we have sigma to the fourth power from here, and we have our denominator 2 sigma squared dx. Now using the exponential rules we can separate the terms here, this term and that term on the power of e with the common denominator 2 sigma squared. So we can separate it as e to the negative x minus sigma squared, the quantity squared, times e to the sigma to the fourth, that they have the common denominator 2 sigma squared, 2 sigma squared. This term here has nothing to do with x, it is not depending x, so we can pull this in front of the integral sign after we simplify. Sigma to the fourth divided by sigma to the second is sigma to the second. So we have e to the 1/2 sigma squared. So expectation of y turns into e to the 1/2 sigma squared, then integral from negative infinity to positive infinity, 1 over sigma times 2 pi, e to the negative x minus sigma squared over 2 sigma squared dx. If you observe that this expression here is the PDF of normal distribution with the parameter sigma squared as our mu, because here x minus sigma squared, x minus mu, so our mu turned into sigma squared. As we said, mu is just a value, just a number. It can be sigma squared. So here our parameter is sigma squared. But no matter what it is, the PDF over the entire region is equal to 1 using the properties of PDF. So this expression is equal to 1. So our expectation of y turns into e to the 1/2 sigma squared, but our y is the log normal with the parameters 0, sigma squared. So we can put this in our toolbox here because we're going to use it. So this was the expectation for log normal of y with the mu that is 0. Now let's find the general that is not equal to mu. So we begin again with the definition of expectation. We said that it is equal to e to the x in our case because our y is equal to e to the x, where x is normally distributed. And that is, by definition, is equal to integral over the domain g of x times f of x, sigma times square root of 2 pi e to the negative x minus mu, the quantity squared, over 2 sigma squared dx. Now we're going to apply change of variable to solve this integral. So let y be x minus mu here. So let y be x minus mu. Then if we solve for x here, then x will be equal to y plus mu. And dx will be the derivative of this. Derivative of this is just dy. And mu is the constant, derivative of mu is 0. Now we're going to rewrite everything in terms of y. So we have integral from negative infinity to positive infinity. We have e to the x. Instead of x, we're going to write y plus mu. And we have 1 over sigma times 2 pi. And e to the, instead of x, we're going to write again y plus mu. And we have negative mu here. Quantity squared over 2 sigma squared. And instead of the x, we're going to write dy. We also need to check the limits of the integral. Here, when x is equal to negative infinity, when x is equal to negative infinity, here our y will be equal to still negative infinity. And when x equals to positive infinity here, again y equals to positive infinity in this equation. So limits of integration did not change, but you have to check it. Now let's do necessary simplifications on the integral here. Negative mu and positive mu cancels out. So we have expectation of y is equal to, from negative infinity to positive infinity, e to the y plus mu 1 over sigma times 2 pi under the radical, e to the y squared over 2 sigma squared dy. Here we can separate the powers of e using the exponential rules as e to the y times e to the mu, and we can pull e to the mu in front of integral sign because it's just a constant and not depending on y. So what we have is e to the mu integral from negative infinity to positive infinity, e to the y times 1 over sigma times 2 pi, e to the y squared over 2 sigma squared dy. If you realize that this expression is exactly what we derived above when mu was equal to 0. So our expectation in that case was e to the 1/2 sigma squared. So instead of this integral, we can write e to the 1/2 sigma squared, because that was the expectation when mu equals to 0 with exactly this PDF. So our expectation in general when mu is not equal to 0 will be e times mu times e times 1/2 sigma squared. And using the exponential rules, you can compact this by adding the exponents. So mu plus 1/2 sigma squared. So this is the expectation of log normal distribution in general. So this was method 1. In method 2, we're going to use direct application of log normal distribution. So let x be log normal with the parameters mu comma sigma squared. Then our PDF will be this. Expectation, by definition, is equal to integral over the region x times the PDF f of x dx. So let's apply the definition of expectation to our log normal distribution PDF. So expectation of x will be equal to integral. Here our domain is from 0 to infinity because logarithm is defined from 0 to infinity. And our mu is from negative infinity to positive infinity, and our sigma is greater than 0. So let's rewrite using this definition. X times the PDF, which is 1 over sigma times 2 pi, e to the negative ln of x minus mu, the quantity squared, divided by 2 sigma squared, all over divided by x dx. We can simplify this x and that x, and we can use change of variable. So let y be equal to ln of x. So we call this ln of x y. Then if you raise both sides on the power of e to the ln of x is equal to x using the logarithmic rules, then x will be equal to e to the y. And derivative of this, which is dx, will be equal to e to the y dy. Now let's write everything in terms of y and check the limits of integral. So our expectation will be equal to integral when x is equal to 0 in this equation. Our y will be equal to negative infinity because e to the negative infinity is equal to 0. If you check the graph of e to the x, if we go to negative infinity, e to the x goes to 0. If we go to positive infinity, then e to the x goes to infinity. And here, when x is equal to infinity, y goes to infinity using the graph of e to the x. Now we take care of the limits of integration. Now let's rewrite everything in terms of y. We have 1 over sigma times 2 pi e to the negative, instead of ln of x, we're going to use y minus mu, the quantity squared, divided by 2 sigma squared. And instead of the x here, we're going to write e to the y times dy. So this is what we obtain at the final step. Our integral is exactly the PDF of normal distribution with the parameters mu comma sigma squared. So we can rewrite our integral as e to the y, and instead of this integrand we can write f of x, which x is the normally distributed with the parameters mu comma sigma squared. Now we're going to use the definition of expectation of a function. If we have a function like g of x times f of x, which is the PDF, that is the expectation of the function. So we can express this whole integral as the expectation of e to the y, which is our g of x. So this is like our expectation of g of x using this definition here. Now expectation of e to the y looks almost like moment generating function. Moment generating function, let's recall, is equal to, which is mx of t, is equal to expectation of e to the ty. So we are missing t here only. If our t value is equal to 1, then this is equal to that. And moment generating function for normal distribution is equal to e to the mu t plus 1/2 sigma squared t squared. We can use this information here. And if our t value equals to 1, that is equal to expectation of e to the y, so we can make our t values here 1 and our t value here 1 to obtain the expectation of e to the y. So expectation of e to the y is equal to e to the mu times 1 plus 1/2 sigma squared times 1 squared, which is going to be e to the mu plus 1/2 sigma squared. So this is the expectation of log normal distribution, because expectation of e to the y is equal to expectation of e to the y times f of x, which is our normal distribution. Now, using either method 1 or method 2, we can derive the variance of log normal distribution. I would like to continue with method 2, but if you prefer continuing with method 1, you can derive variance from there as well. Variance by definition is equal to expectation of x squared minus expectation of x, the quantity squared. We know expectation of x that we have just derived. Now we need to derive expectation of x squared to use in this formula. Expectation of x squared by definition is equal to integral over the region, which will be from 0 to infinity in our case, because our PDF is supported on 0 to infinity, x squared times PDF, which is 1 over sigma times 2 pi e to the negative ln of x minus mu, the quantity squared, divided by 2 sigma squared all over x. So we can simplify x squared and x, so we have here extra x term. Now we can use change of variable. Let y be equal to ln of x. Then x will be equal to e to the y if you raise to the power of e on both sides. Then the x will be derivative of this, that is going to be e to the y dy. Now we can write everything in terms of y, and we know that our x is e to the y. So expectation of x squared will be equal to, and our limits of integration will be negative infinity to positive infinity, as in the previous case. When x is equal to 0, y is negative infinity. When x is equal to positive infinity, then y is positive infinity. So instead of x here, we have e to the y, and we have 1 over sigma times square root of 2 pi. E to the negative, instead of ln of x, we have y minus mu quantity squared over 2 sigma squared. And instead of the x, we have e to the y dy. So this is the expression we obtained from the final step. Now we can merge e to the y times e to the y by adding the exponents. And the rest here is identical with the PDF of normal distribution, where x is with the parameters of mu comma sigma squared. So we can use f of x here instead of that integrand, where x is normally distributed with the parameters mu comma sigma squared. Here we're going to use the definition of expectation of a function again. This is our g of x, and this is our f of x. So that is equal to expectation of g of x. So let's compare this with the moment generating function in general. Moment generating function is equal to expectation of e to the tx. In our case, our variable is y, ty. So this expression is equal to that expression when t is equal to 2. So instead of t, if we use 2, this expression is equal to that expression. And moment generating function of normal distribution is equal to e to the mu t plus 1/2 sigma squared t squared. So let's place t as 2. Mu, 2 mu plus 1/2 sigma squared times 4, so that's going to be 2 sigma squared. So we have e to the 2 mu plus 2 sigma squared. Now this is expectation of x squared. Now we're going to plug this in our variance formula. We found expectation of x in the previous section. We found expectation of x squared now, so we can place them in our variance definition. So our variance of x for log normal distribution will be equal to e to the 2 mu plus 2 sigma squared minus e to the mu plus 1/2 sigma squared squared. So squaring this means distributing this into terms. So let's simplify. We have e to the 2 mu plus 2 sigma squared minus e to the 2 mu plus just sigma squared. Now we have common expression e raised to the 2 mu plus sigma squared that we can factor out. So e raised to the 2 mu plus sigma squared. If we factor this from the first expression, we obtain only e raised to sigma squared, because sigma squared plus sigma squared will give us 2 sigma squared here. And from the second term, we obtain just 1. So this is our variance for log normal distribution. Now let's derive the nth moment of log normal distribution. Let's begin with the definition of the nth moment. Nth moment is the expectation of x raised to the n power. And expectation by definition is the integral over the region. In our case, our PDF is 0 to infinity. X to the nth power times the PDF. Here we are going to apply change of variable. So let y be equal to ln of x. Then x will be equal to e to the y if you raise to the power of e on both sides. And dx will be the derivative of this, which is e to the y dy. And here we can also simplify x to the n divided by x is equal to x to the n minus 1. We just subtract the powers. This is x to the first, n minus 1 raised on x. Now let's rewrite everything in terms of y. And our limits of integration turns into negative infinity to positive infinity. When x is equal to 0, then y is negative infinity. When x is equal to positive infinity, then y is equal to positive infinity, using the graph of e to the x. Now we have x raised to n minus 1 times the PDF. Instead of ln of x, we have y, and instead of the x, we have e raised to y. Now we also replace x with e to the y. So instead of x, we have e raised to y. Now we can distribute this inside and merge with e raised to y. So expectation of x raised to n will be equal to e to the yn minus y, and we have here plus y, times this integrand here. And if we simplify, y cancels y, and this integrand is exactly our normal distribution PDF. So using the definition of expectation of a function, this is our f of x and this is our g of x. So this is equal to expectation of g of x, which is expectation of e raised to yn. Now let's compare this with moment generating function. Moment generating function by definition is equal to expectation of e raised to the tx. In our case ty, because our variable is y. This expression is equal to that expression when t is equal to n, because it will be ny. So we know the moment generating function for normal distribution, which is equal to e raised to mu t plus 1/2 sigma squared t squared. And here, instead of t, if we place n, we find the expectation e raised to yn. So the nth moment will be equal to e raised to mu n plus 1/2 sigma squared n squared. So this is our nth moment. Thank you for watching. If you like this content, please subscribe my channel to support these kind of contents. Thank you.